Hello and welcome to another video on tolerance stackup analysis with GD&T position. So here we are going to do a tolerance stackup analysis to find out what is the worst case gap between this pin and this sidewall on this component over here. So this is the GD&T drawing. Using the GD&T drawing, we'll be creating the loop diagram of the tolerance stackup analysis and we'll be finding out what is the worst case gap. What is the minimum and maximum gap which can be achieved between this pin and this sidewall on this component based on this drawing. So this is a problem of intra-part tolerance stackup. It is within the part itself. We are stacking up the geometrical variations which are created and hence finding out this specification. So let us understand the drawing first. First, the primary datum feature A, which is at the base surface of the part, the bottom surface of the part, that is primary datum feature A, which has a flatness control of 0.05. And then secondary datum feature B is a surface which is perpendicular to datum feature A, which is the back surface. So this surface at the back, that is the datum feature B. The size or the height of the component is controlled by this 24 plus or minus 0.15. And then there is a width feature of size. This width, internal width from here to here is 34 plus or minus 0.15, and that width feature of size is attached with the perpendicularity control. So that width, the center plane of that width should be perpendicular to within a tolerance zone of 0.08 with respect to datum A and datum B. So it should be perpendicular to datum A as well as datum B within a tolerance zone of 0.08. This width feature of size is datum feature C. Then let's have a look at the center pin, which is this pin over here, shown over here in the top view. This pin is having a size, nominal size of 15 and a size tolerance of plus or minus 0.1, and that is being controlled with respect to its position within a cylindrical tolerance zone of 0.2 with respect to datum features A, B and C. So the datum reference frame has been established A, B, C, and with respect to that, the position of this pin is being controlled. So there is a basic dimension originating from datum B, 27.5, which is locating this hole, and in terms of locating in the transverse direction, it is 0. So the basic dimension is 0 because it is at the center. So let's have a look at the loop diagram to find out the gap. Here is the gap shown over here, the question mark, the red color arrow, that's the gap we need to find out. So we can start from here, from this surface, go towards the center plane of the width. So there are two lines over here. There are two center lines. One center line is for the center plane of this feature of size width, this width, and this center line indicates the center axis of the pin. So from this surface, the edge, we move to the center plane of the width. Then from that center plane of the width, we move towards the center axis of the pin, because the center axis of the pin will not always align with the center plane of the width. Hence, there will be a variation there, and that is indicated by the variation number 2. Then from the axis of the pin, we go towards the edge, which is nothing but the radial variation of the pin, that is specification number 3. So it's very simple. Only thing is we need to differentiate between 1 and 2, the variation from the edge of the width to the center plane of the width, and from the center plane of the width to the center of the pin. So this is the loop diagram. So the first specification is the half width, half of size dimension shown over here, which is 34 plus or minus 0.15. We go from this edge to over here, center plane. Then positional deviation of pin from center plane of width. The positional deviation of pin from center plane of width, that is specification number 2. Then radius size of the pin, change in radius size of the pin, half of diameter, that is specification number 3. And the gap to be calculated is over here. We need to calculate this gap. An important disclaimer over here is that we are not going to consider the orientation deviations in this stack up. So neglecting the orientation deviations, we are only going to consider the positional deviations and the size deviations in this tolerance stack up to make it simple. Let us find out the individual specifications, the dimension and the tolerance value for each of those 1, 2, 3. So here is the drawing which shows 1, 2, 3, 3 types of deviations, and here is the sign convention. If the arrow is going from right to left, negative; arrow is going from left to right is positive. So let us consider the first deviation. First deviation is the half width or half of size dimension 34 plus or minus 0.15, half of that is 17 plus or minus 0.075. So this dimension over here 34 plus or minus 0.15, half of that is 17 plus or minus 0.075, which is specification number 1. Specification number 2 is the positional deviation of pin from center plane of width, which is nothing but this over here, this feature control frame, positional control feature control frame. So the radial positional deviation allowed from basic 0 is 0.2 divided by 2, that is plus or minus 0.1. So this specification number 2 does not have a dimension, it only has a tolerance which is plus or minus 0.1, which is the positional deviation. Specification number 3 is the radius size of the pin, the variation in the radius size of the pin, half of diameter. So diameter is 15 plus or minus 0.1 specification. So half of that is 7.5 plus or minus 0.075. So that is the radial size deviation allowed. So then we put all of this into the table. So half width is minus 17. The directions are as per the sign convention. Since the first specification is moving from right to left, it is negative as per this. So minus 17. Then for the second, the dimension is 0, only tolerance plus or minus 0.1. For the third, the radial size deviation, it is going from left to right, so it is plus. So plus 7.5 plus or minus 0.075. Now adding these two, minus 17 plus 7.5 is 9.5, minus 17 plus 7.5 is 9.5, and then adding all of the tolerances, 0.075 plus 0.1 plus 0.075, that amounts to 0.2 plus or minus 0.2, which means that the gap specification, this specification is 9.5 plus or minus 0.2 based on the stack up as created in the loop diagram. So from that we can calculate the maximum width and the minimum width. So 9.5 plus 0.2 is the maximum width. Worst case gap is highest worst case gap is 9.7 and lowest worst case gap is 9.3.